Okay, so I'm just going to go through the first portion of notes in case you were absent or didn't get to fill in everything that we did the first portion of this unit. So our second unit is going to be all about the atomic structure. We have some review where the atom is, of course, our smallest unit of matter that we can measure, and it has elemental properties. And what we're able to do is identify using our periodic tables which element we're looking at, and being able to kind of deduce what the numbers of the subatomic particles that are in those particular atoms. So just going through some general symbols. Based on our PhET simulation, we were able to identify what each of these three subatomic particles were able to contribute to our atoms. We know that the electrons are in what we consider orbitals or orbits. Those are those rings that were around the nucleus. And of course, the nucleus is where 2 out of 3 particles reside. That's what gives it the mass. It's very dense, filled with protons and neutrons that weigh a certain amount. Because the electrons are outside, they don't contribute to that mass. They are much smaller than the protons and the neutrons are themselves. However, the electrons do provide a negative charge, and the protons provide the positive charge. And neutrons don't have a charge. Neutrons are neutral. And similarly, electrons, like we said, don't contribute any mass, but the protons and the neutrons do. How do you find out how many? We said that atoms are electrically neutral, which means that when we're talking about neutral atoms, the number of electrons are equal to the number of protons that are present, because they have to balance each other out effectively. The protons are the atomic number, and we saw that the atomic number we can see in our periodic tables. It's labeled, and each element has its own identity or identification number, which is this atomic number. So this is the identity of the element of which the atom is that we are representing. And last but not least, the neutrons, we do have a mass number as well. A mass number based on how many protons and neutrons are inside that nucleus. And all we have to do is take the mass number, if we know it, and subtract the protons from it to find the neutron amount. So we did a couple examples here where the first one is done for you. We know that the atomic number, the protons, and in neutral atoms, the electrons should all be the same value. So atomic number, we said, was the number of protons. That's the identification. So we can put that they are positive, electrons are negative. The mass is protons plus neutrons, and the neutrons is the mass minus the protons. Of course, that's mass number. So when we're going through, we see that sodium has 11 protons, which again is its atomic number, which is why we know it's sodium, because that's the identity. It also has 11 electrons because the positives and negatives have to cancel each other out. And then neutrons we get based on the mass number minus the number of protons there. So if we did something for K, which is potassium, we find potassium on our periodic tables. We see that it has an atomic number of 19, which means it has 19 protons. 19 electrons is filled in already. And we do the neutron similar here to get 20 neutrons inside that nucleus with those 19 protons, which gives it that mass of 39. Number 38, that is strontium. All right, per our periodic table. The neutrons now we have, so instead of working backwards to find the neutrons, now we can just take the neutrons and the proton amount and add those up to get our mass number as a total value. So that is 38 protons plus 50 neutrons. That gives us a mass number of 88 here. Fluorine is number 9, which means it has 9 protons, and of course 9 electrons, because those have to balance out in our neutral atoms. And we get 19 here because 9 plus 10 is 19 there, neutrons and protons. And last but not least, gold. Gold is Au. Again, a lot of these symbols come from the Latin names, so sometimes they don't correspond with the letters that are in the American names for all these elements. But gold is number 79, which means it has 79 protons and therefore 79 electrons. And of course, we take 197 minus 79, and we get 118 as the neutron amount. So the significance of doing this, or at least being able to figure out how many subatomic particles are within an atom for a particular element, is so that we know where things should reside when we draw them out using our Bohr model. Now, a Bohr model is just a simplified model of what an atom looks like, based on kind of like the PhET simulation, where we have a nucleus and then we have these places where electrons exist. So the electrons exist in those orbitals, right? Or what we call sometimes shells using this model. And we see that the electrons specifically have to be put into certain spaces. And the first shell can fit 2 electrons. And that's because the shells correspond with the period or rows. So we can write that in. So shells equal the period or the row number on the periodic table. All right, and this is what we call energy levels. Energy levels are these shells. And so as we increase the further we go down the periodic table, the more energy levels that exist, because the more electrons we have to fit. And so the energy levels then therefore increase as we move further away from the nucleus, as you can kind of see with this example here. So similar to before, there are 8 electrons that can fit in the second shell always. The third shell is a little weird. We can fit only 8 at first, and then we enter the 4th level, which is the 4th row. But then what we'll see later on this unit is that you can actually go back into the third shell and add a couple more for a total of 18. So we'll talk about that a little bit more later this unit. And we talked about valence electrons. So we know that in a neutral atom, the number of electrons equals the number of protons, right? They have to balance each other out. And then we get these based on where they are situated in certain elements, atoms. We get certain valence electron numbers, and these are the most important electrons, which are the outermost electrons that exist or that reside in the furthest shell. Right, so outermost, and why these are so important is that those are the ones that are going to eventually either increase in number or actually decrease in number based on what our atoms innately want to do. And that's going to get into a little bit later on this unit, what we're going to talk about in terms of ions as well. But we have this whole middle group here, these elements over here, on our periodic tables that we say that they're kind of like secondary groups. The main groups that we want to focus on are the ones that kind of protrude out up here. And again, a lot of this is this is more intro, a lot of this is going to be explained more when we get to our electron configuration later this unit. But what we can see is that on our periodic tables, we have group number 1. So group number 1 corresponds with the first column, and we say groups instead of columns just to differentiate those. We get 2, and then you see we get 3 through 12 right here. So groups 3 through 12, we don't associate with valence electrons because of the nature of some of those electrons, or all of those electrons, wanting to go backwards into previous shells. And so we go through and we end up with 13, 14, 15, 16, 17, and 18 from our periodic table. And those are the other main groups of electrons there. But what you notice is a pattern here that each of those groups have the same number of valence electrons no matter which element in that group we're talking about. So this element right here, which if you looked on the periodic table is boron, actually has the same number of valence electrons as aluminum, which has the same number of electrons as, so on and so forth. So that's going to be a repeating trend that we look at here. And going off of that, you can just kind of identify where these elements are. This is iodine. This is phosphorus in group 15. So it's in here. So it's 5 valence electrons. Oxygen is in group 16, so 6. Boron, 3. Potassium is over here in group 1. Nitrogen, just like phosphorus, is in group 5. So, like we said, if they're in the same group, they have the same number of valence electrons in the outer shells. Argon is all the way at the end. That is going to have a full 8. Right? And once we hit 8, we have to restart next row. And silicon has 4. So when we're dealing with drawing these models out, you're going to be given a mass, because I like us to note how many neutrons we also have inside of our nucleus with our protons. So remember, mass is protons plus neutrons. So I'm going to tell you that the mass is 9 here, and you have the average mass on your periodic tables. What we usually do at the early going is work with the most or the closest whole number and round those decimal values by. And we'll talk about why it's a decimal later on. But right now, let's work on saying that this beryllium atom has a mass of 9. And that means that inside of our nucleus, so all of your atoms should have a nucleus that has a certain amount of protons and a certain amount of neutrons in it. Knowing the atomic number is 4, so we can say the atomic number equals 4. That tells us we have 4 protons here. I'm going to put that to the side. And we then know that we have 5 neutrons. Why do we know that? Well, because this total has to equal our mass number, right? Protons and neutrons make up the mass. And now we need to know where to put the electrons. It's not enough to know that since this is a neutral atom, we will have 4 total electrons to balance out those positives, but we need to know where they are. So beryllium is actually in this second row. It's actually this one right here. And when you're talking about how many shells you need, you have to effectively read the periodic table like a book, and you can see that in this first row, there's only 2 elements that are present there. And that tells you that in the first energy level, or the first shell, only 2 electrons are able to fit. So we'll put 2 electrons there on that outer shell. And then we move on to the next row, which is where beryllium is. And because beryllium is in that second row or period, we know that we're going to need a second energy level, a second shell. And then I think, okay, well, how do I know how many electrons go there? Well, beryllium is the second element in its row or in its pyramid, which means as a neutral atom, it will have 2 electrons in that outermost shell. And that provides us with the complete Bohr model here. And sometimes you can use dots to represent all the electrons. I think it's a little bit easier to just write the numbers there. We'll talk about dots a little bit lower on this portion of the notes. But then we look at the valence electrons, and remember, the valence electrons are the outermost. So I see that beryllium has 2 electrons in that furthest shell, and that is something that we can check because beryllium is in group 2, which all of those elements in group 2 have 2 valence electrons. So effectively what we did was prove that that pattern holds up. Going to carbon, carbon has an atomic number of 6, which means that, and we'll say that the mass of carbon here is, we're working with the 12 mass of carbon version, so to speak, isotope. That's going to be a term that we're going to talk about. But always have to start with a nucleus that has protons and neutrons in it. Right? That's not a PT, that's a P as a positive for proton. And I know that the atomic number is 6, which means that I have 6 protons here, and I'm going to put 6 protons up here. And I should also have 6 neutrons, and that's not because they always need to cancel each other out, right, as we can see from above, but it's because the mass is 12. And I know that protons plus neutrons should give us the mass number. And now I know that I need 6 electrons to balance out those 6 protons there in the nucleus, and now I have to figure out where they are going to be located. Well, carbon is, again, just like beryllium, in the second period, in the second row. And so that means that we should have 2 energy shells, 2 energy levels where these electrons are going to exist. Carbon is actually right over here. So we know that in the first shell, we can only fit 2 electrons. And then we have to move on to the next. And so I count 1, 2, 3, until I hit carbon, which is 4. So that tells me that carbon is going to have 4 electrons in that second shell, which also means that carbon has 4 valence electrons. And the group number on the periodic table is 14, which checks out, right? All of those in group 14 should have 4 valence electrons, of course, until you start getting down to this portion right here. And again, we are going to talk about all of those different exceptions, so to speak, because chemistry does have quite a few exceptions, unfortunately, that we're going to always have to abide by. Lithium, the atomic number is 3, which of course means that in its nucleus, it's going to have 3 protons. If I'm talking about lithium with a mass of 7, then I would have 4 neutrons. And then I say, oh, lithium, yet again, is in group, or in period 2. So I'm going to have 2 of these shells. You'll see that I'm using a dotted line here for the energy shells. I just want you to be able to distinguish between what your nucleus is and what those energy shells are, because electrons don't exist on the nucleus, right? I can't put 2 electrons there because they are outside of the nucleus. So that's why we use a solid line to represent the nucleus that we're drawing, and then dotted line for the energy shells. Just like before, I can fit 2 electrons. That takes care of the first row right here. And then lithium is the first element in the second period, which means it has 1 electron there. And that tells us that we have 1 valence electron because there's only 1 in that outer shell. And it is in group 1, and so as you can see, all of those in group 1 will have 1 valence electron. So all of these elements in that group are always going to have that same number of valence electrons. The only difference is they're going to have a lot more energy levels inside to hold other electrons that are there the further we go down the periodic table. And then, of course, we didn't talk about this in class, but we're going to talk about it when we meet next. We have these nice little Lewis dot diagrams, which Lewis dot diagrams are a simplified way to express how many valence electrons, and start using shorthand notation, an atom of a particular element has. right? And remember, atom means atom as in neutral. Something like, an example, lithium, let's kind of just use the ones above. Beryllium, we said, has 2 valence electrons. So when I draw it, I'm going to actually use dots to represent those 2 valence electrons. And you'll notice that I didn't pair them up. So what you should do when you're doing these Lewis dot diagrams to show just the valence electrons, I usually like to start with the first one at the very top, but each element effectively has 4 sides to it. So you're going to fill in all the sides until you have 4 that are alone, and then you start pairing beforehand, or you start pairing after when you need to. So you're going to start with electrons by themselves, pair when all sides have 1 dot. All right, so beryllium looks like this. If we wanted to do carbon's Lewis dot would look like this. So it's the symbol, and then how many valence electrons there. Lithium would look just like this, right? But then what if we had something past carbon? Because as we can see, carbon and these groups don't really match what we have on a periodic table. This is another way to represent those. But I like using what you have on the periodic table. So once you pass that middle part, this is actually group 13. This is group 14, 15, 16, 17, and the noble gases are 18, right? So once you get past group 14, you'll see that all group 14s are going to have those 4 electrons. That gives just 1 per side. But let's say we wanted nitrogen. Well, nitrogen is in group 15, which has 5 valence electrons. So I'm going to put these in just around, and then I'm going to start doubling them up. Right? If we wanted fluorine, which has 7, we would make sure that we had 1 dot on each side and then start doubling up until we hit 7 there. So you'll never have more than 8 dots here because those are all the noble gases, which, again, we're going to talk about a little bit more formally later on. But that is the extent of the notes that we had covered in class. So this should at least help you go through and fill in anything you missed, and we will have assignment 2.02 and 2.03 that go along with this set of notes, particularly being able to identify the number of those subatomic particles within an atom for a specific element, and then drawing our Bohr models here. That'll be more 2.03. All right, so if you have any questions, please feel free to bring them with you when we next meet, and I hope this helps.